So one says, what's the greatest common divisor of 60 and 18? Did anyone figure that out? Or you can just figure it out right now? Yeah. Mason? 6? I think it's 6. Okay. There. Other people agree? Yeah, so 6 is correct. My guess is you may not know how to do that second problem, right? It says, what's the greatest common divisor of 7,169 and 7,811? Did anyone figure that out? So you could sit there like trying things and seeing what divides both of them, but that's going to suck. So maybe by the end of this class, if we get there, or pretty soon, we will be able to actually answer that question. Or we'll have an effective way of answering that question that doesn't involve just like guessing. So we're going to talk about greatest common divisor. And if we get there, hopefully we will, something called the Euclidean algorithm. Okay, so kind of as a warm-up, talk about something that we need to talk about. I'm going to make a graph, and I'm going to make one node for every natural number, and if x is less than or equal to y, then we're going to draw an arrow from x to y. Okay, but if x is less than or equal to y is less than or equal to z, I'm going to omit some arrows because they're boring. So we don't bother drawing an arrow from x to z, because there will be an arrow from x to y, and there will be an arrow from y to z, and so we won't draw the arrow from x to z. It'll just kind of be implicitly because you get from x to y to z. So this is pretty simple. What does this look like? Well, it looks like I've got 0 down here. I've got 1, and because 0 is less than or equal to 1, I can draw an arrow like this. Right? I guess technically I should have like an arrow from 0 to itself. Right? But I'm not going to draw that one either. I guess I'll say that. Don't bother drawing. Even though, of course, x is less than or equal to itself, I won't draw a little arrow. And then here's 2. There's an arrow from 1 to 2 because 1 is less than or equal to 2. And there should conceptually be an arrow from 0 to 2 also, but I'm not going to draw that because 1 is in between, so I don't. Right? But this is what it's going to look like. This is very boring. It just looks like this. Dot, 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 forever. Right? And this is how we're used to thinking of the number line. If you have a bunch of numbers, here I've drawn it, kind of on its end instead of sideways, but there's a bunch of numbers, they're in order. Numbers that are less are on the left, and numbers that are greater are on the right. Make sense? So why did we do that? Well, let's do the same thing, and I mentioned this before, I think, that less than or equal to and the divides relation actually have a lot in common. So less than or equal to kind of has to do with addition, and divides has to do with multiplication. So we're going to do the same thing. Now do the same thing, but with x divides y instead of x less than or equal to y. In other words, right, I'm going to have a node for every number. If x divides y, I'm going to draw an arrow from x to y. And if x divides y divides z, I'm not going to bother drawing an arrow all the way from x to z. I'll just have like 2 arrows in a row. Okay, so what does this look like? This looks much more interesting. So I'm going to make some space here. So I'm going to put 1 here at the bottom. And I'm going to put like 2 here. Okay, well, why am I drawing it the way I'm drawing it? Well, I kind of have an idea what it's going to look like here. So 1 divides 2, right? So I put an arrow from 1 to 2. I mean, 1 divides anything, right? I'm going to put 3 here. 1 divides 3. And I'm going to put 6 up here, right? Because 2 divides 6, right? 6 is even, and also 3 divides 6. So I'm going to draw an arrow from 2 to 6, arrow from 3 to 6. Right? I'm not going to put. I could put an arrow from 1 to 6, but I don't need to because I already have an arrow from like 1 to 3 and 3 to 6. Okay. Where do you think I should draw 4? I mean, I could put 4 here, right? I could say 1 divides 4. Yeah, but right. But 2 also divides 4. So really, I don't need to draw that arrow from 1 to 4. I need to draw an arrow from 2 to 4. So maybe I'll put the 4 over here. 2 divides 4. Well, I'll put 5 here. And then maybe here I'm going to put 10. Because 2 divides 10, 5 divides 10. And here I'm going to put 15. 3 divides 15, 5 divides 15. You know, I can put like 7. I already have 6 over here. 7 is going to go over here. 8, I guess, should go like up here. Right? And, you know, I guess I'm going to have like, let's see. That's going to have like 30. 30, I guess, goes somewhere like this. It's actually 6, 10, and 15 all divide 30. 60 can go here. Let's see. Oh, we had 60 and 18. So I have 60 on my in here. Where should 18 go? Uh, 18 is 2 times 9, right? So I could draw like put a 9 here. And 18 is up here. And 9 divides 18. 6 divides 18, right? And yeah, I guess I don't need to put anything else, right? Because I got. Anyway, I mean, of course, this is going to be infinite, and it's going to, you know, lots more stuff going up forever. You notice, like, the way we're drawing this, all the prime numbers are showing up on the bottom, right? Because those are the only thing that divides a prime number would be itself, but we're not drawing the little loops, and 1. So 1 is at the bottom. Anything else that's not prime, right, I don't draw it on the bottom because it's going to be divisible by some primes. So all the things on this level are like the things that are divisible by 2 primes. You know, or I guess 9 should maybe be like right here. So, because 9 is 3 squared. And so on. And like, you know, this level you got things that are divisible by 3 primes and so on. So kind of the higher up you go, the way we're drawing this, the more prime factors that it has. Obviously this looks much more complicated and interesting than the picture we had for less than or equal to. Right? Less than or equal to is super boring, it was just a line. This is not a line. And in some sense this is why studying numbers and number theory is so interesting, because when you're thinking about divisibility and multiplication, there's a very interesting structure there. If you only wanted to study numbers and addition, then there's not much to say, but there's a lot to say here. Here's a question for you. So notice there's actually one natural number, well, there's lots of natural numbers that I haven't put on here, but there might be one in particular that is conspicuously missing, and that is 0. Where do you think 0 should go in this picture? yes, it doesn't divide into anything, that's true. What else?
Everything divides zero.
Everything divides zero, right? So conceptually, I've got like, infinitely many arrows going into it. I mean, there's no top, right? This is infinite, but it kind of goes on infinitely, and then like once you've gone infinitely far, then you put zero after that. Okay, so everything divides zero. Okay, cool. So, another thing I'll say about this, well, say times on layer 1. Right, there's the 1 all by itself. And then composite numbers over here. The numbers generally get bigger the higher up you go, although it's not necessarily true that like if a number is above another number physically on this diagram, that it's bigger, right? Like 6 is up here and 7 is down here, so 7 is bigger than 6 in the usual ordering, with less than or equal to. But with divisibility, it's 6 is up here because it's got 2 factors. But generally, numbers do get bigger as you go up. The greatest common divisor. So can anyone say anything like, so you don't know what greatest common divisor is. Can you say anything about what this diagram has to do with greatest common divisors? Like, here's 18 and 60, and we said the greatest common divisor is 6. What does that have to do with this diagram?
It's like the first node to be shared of the first number.
Okay, yeah, so they like share in the sense of what?
Like going down.
Okay, yeah, or maybe you could say this node they share because from this node I can get to either one. Right, you'll see because this arrow means this divides this, and because divisibility is transitive, that's why we didn't bother drawing all the arrows, because like if 2 divides 10 and 10 divides 30, then of course 2 divides 30. So if I can get from here and follow arrows and get somewhere else, that means this number I started at divides the number that I got to at the end. So the fact that I can get from 6 to 18 and 6 to 30 means 6 is a common divisor of 18 and 30. It divides both of them. But, right, like 2 is also common divisor of 18 and 16. Right, but 6 is like higher up. So it's kind of the highest up point from which I can branch off and reach both of them. So the greatest common divisor of A and B is let's say the highest numbers from which we can reach both A and B. What do you think the least common multiple is? have two numbers, right? The greatest common divisor is kind of the highest up thing that can get to both of them. And then the least common multiple is the lowest thing that they can both reach. Because it has to be, a common multiple means they both divide it, so I can reach it from both of them. And it's the lowest down thing that goes up there. Which is the lowest number we can reach from both. Okay, so for example, the least common multiple of, like, let's say 5, I don't know, 15 and 6. Well, if I just look on the diagram, like, what can I reach from both 15 and 6? I guess I can reach 30, right? Okay. Any other questions about this? I haven't formally defined greatest common divisor and least common multiple. I mean, I guess maybe I kind of have, but I will in a second do a slightly more formal. All right. And this idea of, so we're going to talk a lot about the greatest common divisor, because this is a super important idea that comes up all the time. We're not really going to talk much about least common multiple, because in some sense they're exactly opposites of each other, kind of in the same way that, remember how and or were opposites of each other. And so anything that's true about greatest common divisor, you can kind of, if you flip things upside down, it turns into a true statement about least common multiple. So, and greatest common divisor is more common in practice. Like least common multiple, the only place you use it is adding fractions. But the greatest common divisor, talk about it a lot. So, let me give you an actual definition of greatest common divisor. So let A and B be natural numbers. The greatest common divisor of A and B denoted, we often write it like GCD. Sometimes people even write it just like with parentheses A comma B. I find that confusing because it looks just like a pair. It depends on the context, but I usually write GCD. Is a unique number such that for all natural numbers D, and this definition is a little abstract, so I'm going to talk through it a little bit, but D divides, oops, that's why I did some examples first, but GCD AB, if and only if D divides A and D divides, oops. Think about this a little bit. So this is an if and only if. So let's think about each direction independently. So first of all, in the left to right direction, it says, okay, your GCD, if you have GCD of A and B is some number, if D divides that, then D must divide A and it must divide B also, right? And so, think about it this way. Here's my GCD of A and B in my diagram that I made before. So there's like, there's some path to get to A and there's some path to get to B. I'm drawing it with like squiggly lines because it might not be a single arrow, it might be like a bunch. But it's just like some path that gets me from here to there. And then D, think about the D in this definition. Think of it as being kind of like down here. Okay? So we're saying, look, if D divides GCD of A and B, then D had better divide A and it had better divide B. And in particular, if we choose, like this is supposed to be true for any D, right, for all D. So if I choose D to be GCD AB itself, right, well of course anything divides itself, so that's true. Then this tells me, well, GCD of AB has to divide A and it has to divide B. So that direction is telling me that yes, the GCD of AB really is a common divisor of A and B. It has to divide both of them. The greatest part, like the greatest common divisor, that's the other direction of the if and only if. So it says, look, if you have any D that actually divides both A and B, then that D also had better divide the GCD. It's not possible, you can't have another D up here, right, that divides A and B, but like doesn't divide the GCD, it's like above it. Right, any D that divides A and B has to actually be below the GCD, which means the GCD is kind of the highest up thing that divides them both. So, to summarize, the left to right direction says GCD of A and B really is the common divisor of A and B. And the right to left direction says the GCD of A and B is the greatest common divisor. And I want to point something out here. This is something that people often get wrong, and even a lot of textbooks kind of get it wrong. This definition doesn't say anything about less than or equal to, right? Like the simple less than or equal to does not show up anywhere in this definition. So this word greatest does not mean greater than in the usual sense of like, 3 is greater than 2. It means greatest as in like the highest up in that divisibility diagram that we drew. Okay? Usually that's the same. As we said, like in that diagram, things that were higher up tended to be bigger than things that were lower down. Okay? One place it's dramatically not the same is for 0. And so we'll think about how 0 interacts with this definition. And if you think that the word greatest means greater than or equal to, then you have to say it's undefined for certain things. But we'll see here that we can actually give a sensible definition for 0. Okay. So let's. I'll just squeeze it on down here so we can look at the definition while we're doing some examples. Okay. What is the greatest common divisor of 6 and 10? 2. Yeah, so it's not 3. 3 doesn't divide 10. So 2. What is the greatest common divisor of 2 and 3? 1. Yeah. What is the greatest common divisor of 2 and 4? 2, right. Because 2 divides 4, and 2 divides itself. And so you can see that, like, in general, whenever I have the GCD of 2 things where one actually is a divisor of the other, then the GCD is going to be that one that divides the other. Right? Or, another example, what's GCD of 3, 3? 3, right? And we kind of like to say, is the GCD of A always equal to A? Question mark. Seems plausible, right? We'll come back to that in a second. What is the GCD of 0 and 7? Seven? I'm gonna say 7. Everyone agree? I agree too. 7 divides 7, of course. And 7 also divides 0, because anything divides 0. Oh. Okay, now for the kicker. What is the greatest common divisor of 0 and 0? Okay, you think it should be undefined? Why? Really? Does 0 divide 0? It's been like maybe a week since we talked about this, but right, the definition of one thing dividing another is there exists some integer that you can multiply by it to get the thing. So does 0 divide 0? Like, is there another integer such that 0 times that integer equals 0? Sure, I mean, I can pick anything I want, right? So 0 does divide 0. But really anything divides 0, right? Like 5 divides 0 because 5 times 0 is 0. So 0 would be a common divisor of these, but so is 1 is a common divisor, so is 2, so is 17, right? Any number is a common divisor of 0 and 0. So what's the greatest common divisor? Okay, wrong. Because remember, I said the word greatest here doesn't mean bigger than in the usual sense. It means the highest up thing on that diagram. What was at the very, very tippy top of that diagram? 0, right? So, yes, it does not, right. If greatest here meant bigger, then we would have to say GCD of 0, 0 is undefined, because there's no biggest natural number. But there is a highest up thing on this diagram, right? That's 0. Everything divides 0. So one way to tell whether a programming language is cool or not is to try GCD of 0, 0 and see whether it gives you the correct answer of 0 or if it like crashes or something. I don't actually know. I don't remember what. I'm just kind of curious, but like Python or Java gives you 0. They probably do. Cool. Okay. So let me just greatest. This means highest in not. And okay, I didn't actually talk about this definition, but if we think about this definition. Like if A and B are both 0, then the only thing that works, if I pick any other number for GCD, like let's say, okay, so what if 7 is the GCD of 0 and 0? Well, then I have to find a number D such that D divides 0 and D divides 0 if and only if D divides 7. And that's not going to work, because anything divides 0, but anything doesn't divide 7. Right? The only thing I can pick that will work is if I pick if I pick the GCD to be 0, then it's true that D divides 0 if and only if D divides 0. So it actually fits the definition as well. Okay. You can divide at least LCM very similarly. You just kind of flip things around. Like you flip the direction of the divides relation. So you flip this, you flip these, and you write LCM instead of GCD. I'm not going to do it because we're not really going to talk about LCM much, but you could if you wanted to. So, how do we compute the GCD and incidentally the LCM? So, one way that you probably learned in school, perhaps, is that if you factor the numbers into their prime factors, right, then you can kind of look and see what primes they have in common. So one way is to factor both numbers and pick all the primes they have in common. So for example, going back to example 60, what's the prime factorization of 60? It's 2 times 3 times 5, I think. Right? Yeah, 2 times 5 is 10, 2 times 3 is 6. And then 18 is 2 times 3 times 3. Yeah. So if I pick the primes they have in common, they both have a 2, so I can pick 1, 2. They both have a 3, so I can pick one of those. But that's it, right? I can't use this extra 2 because 18 only has a single 2. I can't use this 5. 18 doesn't have any 5s at all. And I can't use this 3 because 60 doesn't. Well, 60 only has one 3, so I only get to pick one. Right, so that, or 2 times 3, which is 6. That's what we said before was the GCD. Okay. Right, more generally, you can write, A equals 2 to the A2 times 3. So A has a prime factorization, right? It's some number of 2's, which I'll write as 2 to the power of A2. And A2 could be 0 if A doesn't actually have any 2's in its prime factorization, right? Because 2 to the 0 would be 1. So let's just think, yeah, we don't have any 2's. 3 to the A3 times 5 to the A5, 7 to the A7, dot, 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 right? Conceptually, this is infinite, although only finitely many of them only finitely many of these powers will be non-zero, right? So in other words, like for example with 60, I would have a 2 here, and a 1 here, and a 1 here, and all the rest would be 0. So for example, 60 equals 2 squared times 3 to the 1 times 5 to the 1 times 7 to the 0 times 11 to the 0 times dot, dot, dot. Okay, then we can say that the greatest common divisor of, well, if I have some number 2 to the A2 times 3 to the A3, 5 to the A5, 7 to the A7, dot, 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 comma, 2 to the B2, 3 to the B3, 5, 7, dot, 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 equals, well, how many 2's do I want? I'm only allowed, like in this case, right, in this example, I had 60 had 2 factors of 2, but 18 only had 1 2. So I was only allowed to take 1 2 for the GCD, right, because it had to divide both. Okay?
Is that how we would find the GCD of those two numbers?
It's not, no, it's not, I mean, you could. It's not a great way. We'll talk about that in a second, why this is not the best way to do it. This is probably the way that you might have learned in school. There's a better way. But this is the way kind of that you could figure out that makes sense just based on the definition. So, in general, I look at A2 and I look at B2 and I just take whichever one is smaller, because that's the max number of 2's that will divide both, right? So it's going to be 2 to the power of, well, whatever the minimum is of A2 and B2. And same for 3, right? I say, okay, how many 3s can I put in the GCD? It's going to be whichever is the smaller power, whichever has the smaller number of 3s. So minimum of A3 and B3, 5 to the dot, dot, dot. Okay. LCM is the same except we use max instead of min. LCM, same, but we use max instead of min. And incidentally, by the way, this shows that the GCD of A and B times the LCM of A and B equals A times B. And I'll let you think about that. I mean, when I say this shows that, I mean, like, well, if you think about it sufficiently hard, it's not necessarily obvious. Think about, like, you know, this expression for the GCD and the similar expression with all maxes for the LCM, and think about what happens when you multiply them, what you would get. That's not really important, though, I just, as an aside. So, yeah, so Gael was asking, all right, so is this how we can compute, going way back to, oh, I didn't actually write it on the thing, right? So the other example was, you know, what is the GCD of 7169 and 7811? Right? Could we use this method to find the GCD of those? Well, we can, but what would we have to do first? What would be the first step if we wanted to use that method of computing their GCD? Nora? Yeah, we'd have to factor them, right? We'd have to first write them in terms of their prime factors, then we could just look and see what they had in common. Does anyone know the prime factorizations of these numbers? I mean, of course we don't know that off the top of our heads. You can sit there and like try dividing it by a bunch of primes and like see. And of course we know it from the other day that you only have to go up to their square root, so that gives you a limit of like what you have to try. Garrett?
I know 3 isn't one of them.
You know 3 isn't one of them? Very good. All right, so we have a start. Also 2 isn't one of them, right? Yeah. I'm pretty sure, I don't remember off the top of my head, but I'm pretty sure I picked these to be the products of some largish primes, so that it wasn't going to be something obvious like 2, 3, 5, whatever. Yeah, of course. But I'm trying to make a point. But the thing is, it's not just the fact that, okay, I happen to pick hard things here. Factoring in general actually is hard. And I don't mean hard in the sense of, like, hard to understand. I mean, it's very easy. Writing a program to factor some numbers is pretty easy to write a simple program to try to factor numbers. You just have some loop where you kind of go through and you try all the primes. You don't even have to worry about trying primes. Just try every number and just see if it's divisible by something, right? It's hard in the sense of that program is going to be very inefficient. You know, these numbers are not so bad. So these are only like 1,000 something, 7,000, and if you if you wrote a program to factor these, it would finish right away. But you know, even numbers that have a smallish number of digits, like say 12 digits or 15 digits or something like that, like a program to try to factor them by just trying all the divisors is going to take an extremely long time. So once you have them factored, then yes, this is easy. But it turns out that factoring them in the first place is difficult, or it's difficult to do it efficiently. And this is an interesting aside, right? But there's a lot of modern cryptography. So So like, when you go to a website and you're gonna put in your credit card and you see that like it says HTTPS and it's got a little like lock icon or whatever, right? That tells you that your computer is communicating with that website using some kind of encryption, so that anyone that's listening to the bits going by in the middle can't figure out what your credit card number is. Okay? The security of that, in many cases, depends on the fact that factoring numbers is hard and multiplying them is easy. So you can pick some numbers. If I pick the numbers myself, I know what they are, and then I multiply them. If I just give you the result of multiplying them, it's very hard for you to go backwards and figure out what the original numbers were. And that ends up being the basis of a bunch of cryptography. Nobody has proved that factoring numbers is hard in that sense, but if it turns out that it's easy, then that's going to break it means a lot of people can steal your credit card. There are other ways of doing cryptography that don't depend on that, but many of the most common ones do. So this requires factoring, but factoring is hard. I really shouldn't say hard. I mean, people do use the word hard in that technical sense, but let's just say it's slow. That's really what I mean when I say hard. So, the question is there a better way? The answer is yes, and we're going to see it after spring break.
No.
I know, right?
Cliffhanger.
Sorry. Because we only have 5 minutes left. So there is a better way called the Euclidean algorithm, and we're gonna have to prove a few properties of GCD that mean we can actually, even though factoring is difficult, we can compute the GCD of any two numbers, very quickly. I know I've been promising a new module for you, and I'm still going to do that. So my goal is to put it up very soon, and you can look at it over spring break if you wish or not. So it's you. So it's going to be due, the Friday after spring break. So if you just want to forget about it and enjoy your spring break, and then look at it when we get back, then you'll have that week. Fine. But if you want to get a head start and look at it, I will post it in the next couple days, so you can look at it if you wish. Yeah, and I will. If you have questions, if you are working over spring break on past modules or this module, or whatever, feel free to email me. You can't sign up for meetings with me over spring break, but I'll still be checking my email. I'm happy to answer questions about